In this paper, we introduce the vector animation complex. It is a data structure designed to represent animated vector graphics whose topology continuously changes over time. But before describing this structure, let's first convey some intuition about spacetime topology. Suppose an animator wants to animate a single point or vertex in a one-dimensional space. The existing way to achieve this is to define a sequence of keys, Ti, Xi, which are interpolated in time. To animate 3 vertices, you need 3 sequences of keys. We call this paradigm sequential keyframing, since it is composed of sequences of keys, 1 per vertex, or more generally, 1 per degree of freedom you want to animate. But what if you want the number of vertices, or degrees of freedom, to change over time by splitting or merging? We can observe that the spacetime topology of such animation is not anymore disconnected sequences, but a more general graph. Therefore, to handle such a scenario, we need a more general approach to keyframing that we call topological keyframing. The animator first defines a set of key values, which are the same objects as in sequential keyframing, except that they are not ordered in sequences. Then he defines a set of in-between values. Each in-between value is a pair that references to 2 key values to interpolate. In theory, we could apply this concept to animate any kind of values, for instance quaternions. But in this paper, we use it to animate vector graphics complexes, or VGC for short. This introduces additional challenges because a VGC is already a graph in the space dimension. Our data structure, the vector animation complex, is a cell complex immersed in space-time. It is made of 8 types of cells: key vertices, key closed edges, key open edges, key faces, in-between vertices, in-between closed edges, in-between open edges, and in-between faces. A precise definition of all these cells can be found in the paper. In practice, using a 3D view and 3D tools for the modelization of complex examples quickly becomes impractical. Therefore, we have implemented a set of tools to create and edit the spacetime topology directly in 2D. Key cells can be created and edited using standard VGC tools. They are assigned the time selected in the timeline. We can copy key cells at time t1 and motion paste them at time t2. This creates a copy of the key cells and creates in-between cells to interpolate them. The new key cells can be edited to achieve the desired motion. Any in-between cell can be split in half by inserting a key cell. This is the equivalent of inserting a keyframe in conventional animation systems. Note how this keyframing is local, making possible to easily model asynchronous motions with a minimal number of key cells. Another way to create in-between cells is to connect in time existing key cells using the in-betweening tool. For instance, to create an in-between vertex, the user selects 2 key vertices. To create an in-between edge, the user selects 2 key edges. If more than 2 edges are selected, they are organized in paths and cycles. When possible, existing in-between vertices are used instead of creating new ones. It can also be used to make an edge grow or shrink to a vertex. Finally, it also works for closed edges. Key cells can be drag and dropped in space, but also in time, within a time interval determined by its incidence in between cells. This is very useful to refine the timing of the motion. Finally, we provide tools to control the depth ordering of cells. Here, we first create an animated ribbon decomposed into 6 key faces and 4 in-between faces. Then, we use the raise tool on a few faces to depict a depth ordering that is local both in space and time. Now, we present some results. We created this example by reproducing 8 frames from a rough pencil test and connecting them with the in-betweening tool. Then, we used the onion skinning visualization to refine the motion and the topological events for smoother results. This bird has been created in a coarse-to-fine fashion. We created first the high-level motion using very few cells. Then, we progressively added keyframes, topological events, then coloring. By duplicating the animation and gluing together the first and last frames, we can achieve a seamless looping motion. Finally, once topological events have been designed, they can easily be reused. Here, we copy-paste a subset of the torus animation, from which can be created the animation of a double torus, which would have been hard to achieve using 3D animation systems. Thank you for watching.